Hello everyone, myself Tanzia Mansuri, and today we are delving into the theory of computation. Specifically, we are exploring here languages and grammar, which is the backbone of computing. So let's dive into and unravel in the fantastic world of formal languages and grammar together. So let's see what are grammar. Grammar in the context of formal language theory and computational linguistics, grammar are used to describe the structure of language. In this case, we are examining a subset of English defined by the set of rules, and this set of rules are called as production rules. So here are 15 production rules described here. The production rule, the grammar provide consists of terminal, which are the actual symbol in the language, and non-terminal, that are the symbol that represent a syntactic category like noun, phrase, verb, phrase, etc. These all are non-terminal. These are the rules, production rules, which are defined here. Now let's see Noam Chomsky theory. Here you can see a man, Avram Noam Chomsky, who was born in 1928. He had given a phrase structure grammar definition. He is the greatest linguistics. So he has given a phrase structure grammar, or simply grammar theory, which is N, T, P, and S, where N represent a finite set of non-empty set of non-terminals. A T is a finite non-empty set of terminals, where N is a finite non-empty set of non-terminals, T is a finite non-empty set of terminals. N implies T equal to 5, that is empty. S is a special symbol which is called start terminal. P is a finite set of terminal that is in the form of alpha implies beta. Now let's see question number 1. In the question number 1, we have given a set of production to show that each of the sentence is a valid sentence or not. So here we have given a set of terminals and non-terminals, which is represented by T and N respectively. The set of terminal T are the sleepy, happy, hare, tortoise. These all are the terminals, and set of non-terminals N are noun phrase, transitive verb phrase, intransitive verb phrase. These all are the non-terminals, and the production rules given here are these. These all are the production rules. So by applying this production rule, we have to show that the sentence is a valid sentence or not. So let's see now. For instance, to validate the sentence "the happy hare run," we followed the production rule, such as sentence imply noun phrase, intransitive verb phrase, article adjective phrase. Noun phrase implies article adjective noun. Noun phrase imply the happy hare runs, and then finally we get our sentence as the happy hare run. Similarly, we can apply production rule to validate the other provided sentences as well. This process demonstrates how the grammar generate valid sentences within the defined subset of English by recursively applying the production rule until we derive into the sequence of terminals. Now, before moving to another question, let's see what is derivative tree. So a derivative tree in the language generated by a context-free grammar, CFG, context-free grammar, that can be represented graphically using an ordered root tree called a derivative or a parse tree. So this is a definition of derivative tree. You can see a table here. This table represents the types of grammar. So here are 4 types of grammar. So these all are the types of grammar here, and I have also shown here the restriction on the production rule of this grammar. Now let's see question number 2. So in the question number 2, we have to construct a derivative tree. So a derivative, here you can see 2 men, John Backus and Peter North, that together give the theory of BNF, that is Backus-North form, which is used to derive a derivative tree for the sentence. So here you can see a sentence, "the happy hare run." In this, the sentence is divided into 2 parts, a noun phrase and intransitive verb phrase. Then the noun phrase is further divided into article, adjective, noun, and then intransitive verb phrase is divided into intransitive verb. So according to our question, the is the article here, happy is the adjective here, our noun is hare, and runs is our verb. So by applying this rule, we have created a derivative tree. Now let's see question number third. In question number third, we have to construct a parse structure grammar that generate a sign, positive or negative or non-negative integer, a decimal fraction, which can be either an empty string or a decimal point. So this parse structure grammar generates signed decimal integer. So according to a specific format which includes positive and negative, a non-negative integer, and optional decimal fraction. Now let me explain you what are all these production rules. So here as implies sign and integer, this production rule generates sign a signed decimal number by combining a sign and integer. Secondly, as imply integer, a sign integer dot positive integer, this production allows for the addition of a decimal fraction to a signed decimal number. Third, it says sign implies positive, this production generates a positive sign. Then sign implies negative, this production generates a negative sign. Then integer implies digit, this production generates an integer starting with a single digit. And then integer implies integer and digit, this production allows for the addition of digit to integer including initial 0. Then positive integer implies integer non-zero, this production generates positive integer starting with non-zero. These all are the representation. So overall, this grammar ensures that signed decimal numbers are generated with the appropriate structure, including the presence of an sign, a non-negative integer, and an optional decimal fraction. Now let's see the BNF of this. So here we have to show the BNF representation of that grammar. So this is basically a BNF representation. This representation describes the structure of signed decimal number, including the presence of sign, an integer part, and an optional decimal fraction. Each non-terminal is defined in terms of non-terminal and a terminal symbol. Now we have to construct a derivative tree for minus 31.7. So here is a signed decimal integer which is divided into a sign, integer, a point, and positive integer. So we have to derive a derivative tree for minus 31.4. So here minus sign is here minus is our sign. Our integer is divided into 3 and 1 digit, where digit is 3 and again a digit is 1. Point is our point here, and a positive integer which is non-zero is our 4. So in this way we have constructed a derivative tree for minus 31.4. Now we have to give production rules in Beckers-Nor form for an identifier if it can consist of one or more lowercase letter. So we have to give a Beckers-Nor form for this. Now I will explain what are the identifier, LC letter, and letters, and this all mean. So basically this identifier which is enclosed in this symbol, it represents that this is a non-terminal with symbol representing an identifier in C. It is defined either as a single letters or a symbol. Now second we will see what is letter S. So this is also a non-terminal symbol which represent either a letter or a symbol. It is used to allow identifier to start with either a letter or an underscore. Now we will see what is symbol, digit, and LC letter and UC letter described here. And UC letter is used to describe an uppercase letter. Now let's see another question. So in this question we have to give production rule in Beckers-Nor form that generate all identifier in C language in letter or an understate that followed by one or more lowercase letter, uppercase letter, identifier, and digit. So here the symbol, that is identifier, letter, symbol, digit, this all I have previously explained you. You can refer to. So several extensions to Beckers-Nor form are commonly used to define phrase structure grammar. In such extension, a question mark indicates that the symbol or a group of symbol inside parenthesis to its left can appear 0 or more once, that is it's optional, and an asterisk indicates that the symbol to its left can appear 0 or more times, and a plus indicates that the symbol to its left can appear 1 or more times. These extensions are the part of Beck's-Nor form. In this question, it was similar to the infix notation, and now in this question we have to give the postfix notation for this for this, and there are the several steps. So for this grammar given, we have to show the postfix notation. In this, we have to find a step used to generate the string. So these all are the sentences and their postfix notation. Now let's see the another sentences. These all are the similar sentences for postfix representation. Question. In this question, we have to determine whether the string is infix expression or not. Infix notation expression, we use parentheses to indicate the order of operation. So for in a sentence x plus y plus z, the string is not generated because there is no parenthesis in this. You can see there is no parenthesis in x plus y plus z, so string here is not generated. Now let's see a B part where a slash b plus c slash d. So in this it is a generated string. This expression follows a pattern: term, add operator, and term, where each term can be further divided into factor, multiply operator, and factor. Additionally, each factor can be enclosed with parentheses. So here expression is starting of the outermost expression, term break down the expression minus n plus p minus q is not generated. This string lacks the required structure of factor enclosed in parentheses. Additionally, there is no provision for alternate addition and subtraction operation without parentheses in the grammar. Similarly, m plus n star p minus q, this string is generated because it follows the pattern expression, multiply operator, expression. So this follows a pattern expression, multiply operator, expression, where each expression can be further broken down recursively. So in this way we have generated all the strings, and we have shown the representation which string is generated and which string is not generated. Now let's see another question. In this question, we have to construct a finite automata, push down automata, and Turing machine which accept string over 0 1 ending with 0 1 0. So here our input strings are 0 and 1. So and we have to generate a finite automata. Firstly, we have to generate a finite automata for the string which ends with 0 1 0. So a string can start with either 0 0 1, but its ending should be 0 1 0. Okay, a string can start with anything, but its ending should be 0 1 0. This is what our question is saying. Here is a state transition diagram in which there are 4 states: Q0, Q1, Q2, and Q3. When one comes on Q0 state, we either stays on Q0 or we moves to Q2. Similarly, when 0 comes on Q0, we move towards Q1. Similarly, when 0 comes on Q1, we either stays on Q1 or we move to Q3. And when 1 comes on Q1, we move to Q2. So our initial state here was Q0 and our final state here is Q3. So in this way, we have created a state transition diagram of finite automata here. Now let's see a state transition diagram for Turing machine. It's similar to that of DFA, that is deterministic finite automata. Here we have taken 6 states: Q0, Q1, Q2, Q3, Q4, and Q5, where Q0 is our initial state and Q5 is our final state. This arrow implies that it is our initial state. So in this way, we have created a Turing machine as well for this. Now let's see push down automata, how we can create a push down automata. Now to construct a push down automata that accept the set of all string over 0 1 ending with 0 1 0, we have to follow several steps. Firstly, we have to start with initial state and a special symbol says z, which is marked into the stack. This is our stack. We will mark this mark the bottom of the stack as z. Now we will reach each symbol of the input string from left to right. transition based on the current symbol and top of the symbol of the state. So for making the state transition diagram, we will take 4 states here: Q0, Q1, Q2 and Q3, and our input alphabets will be 0 and 1. Our initial state will be Q0 and our final state will be Q3. And by applying these all transition rules and transition table representation, we can create a push down automata for the same. Now let's see another question. In this question we have to construct a Turing machine that accept the language 010, 01 star plus. Now we have to construct a Turing machine that accepts the language 01 star plus 10 star. So for creating, so we have to construct a Turing machine which remembers the first symbol and checks that it does not appear afterwards in the input string. So we require two states here, QA and QJ, and our tape symbols are 0, 1 and B. So the Turing machine having the storage capacity will storage facility in state, that is M, will represent in that form. We describe 0 by its implementation description. In the initial state, M is in Q0 and has 0 in its data portion. On seeing the first symbol of the input string W, M moves right, enter the state Q1 and the first symbol says A, it is seen. And M is now in Q and A. If its next symbol is B, M enters in Q1B and accepting state. If the next symbol is A, M halts without reaching the final state, that is 0 is not defined. And third, if the next symbol is A, so if A is 1 and A is 1, if A equal to 0, M moves right without changing state. So we will repeat the step 2 until M reaches QJB on halt. Now let's see our Turing machine for this. So this is the Turing machine which I have previously explained you the steps of constructing this Turing machine. So basically this is the Turing machine. Now let's move towards another. So in this question we have to create a PDA, push down automata, which is equivalent to the following context free grammar. So in this we have given our S can be written as 0BB, our B can be written as either 0S, 1S or 0, and we have to test whether 010 to the power 4 is generated by this or not. So for this we will construct a push down automata which is equivalent to the given context free grammar, and we will test whether 010 to the power 4 is in the language generated in PDF. So firstly we will see what are the states here. Here our states will be Q0, Q1, Q2 and Q3. Our input alphabet will be 0 and 1. Our stack alphabet will be 0, 1 and Z. Firstly we will put Z in our stack, and our accepting state or the final state will be Q3. And by applying this all the transition rules, we will start in states Q0 with stack 0 on the stacks, read the input string, and we will follow the transition of the push down automata accordingly. If the push down automata reaches the accepting state Q3 with an empty state, then the string 010 to the power 4 is in the language. So basically these all were the solutions for the internal test as well as languages and grammar. Thank you for watching. Thank you.